Welcome to the world of deep learning. In this video, we'll explore how deep learning, a branch of artificial intelligence, empowers computers to process data inspired by the human brain. Deep learning models can handle tasks far more complex than traditional machine learning, such as recognizing images, text, and sounds. By the end of this journey, you'll understand the basics of deep learning and how to build your own models. Let's start by looking at why deep learning is so important in the field of AI and how it mimics human thinking to automate tasks that once required manual intelligence. Deep learning is a game changer because it allows computers to think and learn like humans. Unlike traditional machine learning, deep learning models can process unstructured data such as images and sounds. This means we can build AI systems that describe pictures or convert audio files into text instantly. The ability to automate these tasks is what makes deep learning a crucial part of modern AI. As we move forward, you'll see how deep learning replaces manual processes and brings us closer to creating intelligent machines. The heart of deep learning are layers, 3 or more to be exact. These layers act as artificial neural networks, replacing the human brain's neural connections. Each layer helps the model learn from massive amounts of data, making it possible to solve complex problems. But what exactly are these layers and how do they relate to the human brain? Let's dive deeper into the concept of artificial neural networks and see how they form the backbone of deep learning. Artificial neural networks, or ANNs, are powerful and versatile models inspired by the neurons in our brains. They're ideal for tackling complex machine learning problems, from classifying billions of images to recognizing hundreds of languages and even recommending videos to millions of users. Before we explore how computers mimic human neural networks, let's first understand the basics of biological neurons and how they communicate. Neurons are the messengers of the brain, using electrical impulses and chemical signals to transmit information between different areas. Each neuron consists of 3 main parts: the axon, dendrites, and the cell body containing the nucleus. The axon sends messages, dendrites receive them, and the nucleus controls cell activity. Neurons connect with thousands of others, forming complex networks that enable us to perform intricate tasks. This organization is what inspires artificial neural networks in computers. Neurons communicate through chemical compounds called neurotransmitters, which cross tiny spaces called synapses. When stimulated, a neuron sends signals to others, enabling rapid responses, like pulling your hand away from a hot pan. This fast, organized communication is the foundation for complex tasks. In computers, we replicate this process using artificial neural networks, allowing machines to learn and perform tasks efficiently. Inspired by biological neurons, artificial neural networks in computers use basic components called perceptrons. Frank Rosenblatt first introduced the perceptron in 1957, and it serves as the fundamental unit in neural networks. In these networks, perceptrons and neurons are essentially the same, processing inputs and generating outputs. Let's see how perceptrons work and why they're crucial for building intelligent systems. Perceptron receives numerical inputs, processes them, and produces an output. Each input has a weight which the perceptron learns to adjust. The process involves multiplying each input by its weight, adding a bias, a constant, and then applying an activation function to map the result. This activation function allows the perceptron to handle nonlinear data, making it flexible and powerful. Understanding this process is key to grasping how deep learning models learn from data. After processing inputs and applying the activation function, the perceptron generates a numerical output. This output is the result of all the mathematical operations performed. By chaining multiple perceptrons together, we create layers that form the artificial neural network. These layers enable deep learning models to solve complex problems and learn intricate patterns from data. Hidden layers are dense layers located between the input and output layers. They're called hidden because they aren't directly observable, unlike input and output layers. The more hidden layers a network has, the longer it takes to produce results, but it can solve more complex problems. Hidden layers contain multiple perceptrons, each learning different aspects of the data. This structure is what gives deep learning its power and flexibility. Deep learning has revolutionized various industries by enabling machines to process unstructured data like images, text, and audio. Before deep learning, experts manually defined features for tasks such as image classification. For example, identifying a bird required specifying features like wings, beak shape, and feet. This manual process was time-consuming and challenging. Deep learning simplifies this by allowing models to learn features automatically from data. Previously, image classification involved experts defining rules and filters to identify features in animals. For instance, edge detection was used to find a bird's beak, and morphological operations match expected shapes. Each animal required a unique set of rules, making the process lengthy and complex. Deep learning changes this by enabling models to learn directly from data, streamlining the classification process. With deep learning, building AI systems becomes easier. Models can learn from vast amounts of data and perform tasks based on real-world challenges. Whether it's processing images, text, or audio, deep learning adapts to different types of data. Let's explore some practical examples of deep learning applications, starting with image processing and custom vision. Imagine sitting by the beach observing the sunset and the environment. Your eyes act as sensors, capturing the scene while your cognitive system interprets what you see. Human vision is dynamic, adjusting to brightness and focusing on objects at varying distances. This remarkable capability is what computer vision aims to replicate in machines, enabling them to interpret visual information. Computer vision builds methods for image formation and machine perception, mimicking human sensory and cognitive systems. Sensors like cameras capture images, while machine learning methods extract information from them. Modern approaches use deep learning to analyze images, making computer vision a complex yet fascinating field. Let's see how these methods work in practice. For humans, interpreting visual information is easy, but for machines, it's a challenge. Machines require powerful parallel processing and complex control systems to handle large amounts of visual data. This makes computer vision both a demanding and rewarding field as it pushes the boundaries of what machines can achieve. Decade ago, computer vision relied on methods like denoising, edge detection, and texture analysis, without machine learning. Today, AI and machine learning have transformed the field. Image classification is now handled by deep learning techniques such as convolutional neural networks, enabling machines to recognize objects in images with high accuracy. Deep learning models are trained by feeding them large datasets of images and their labels. For example, to classify animals, we show the model many images of birds, rabbits, and cats, each labeled correctly. The model learns to recognize new images it hasn't seen before, making the process of image recognition faster and more accurate. Computer vision is making a big impact in healthcare. Medical professionals use imaging data like X-rays, CT scans, and MRIs to diagnose and treat diseases. Deep learning models help interpret these images more accurately, supporting doctors in making better decisions. While computer vision won't replace healthcare workers, it complements their expertise and improves patient outcomes. Computer vision in medical imaging helps predict and analyze symptoms, monitor blood loss, and detect diseases like COVID-19. For example, COVID-19 uses deep neural networks to diagnose COVID-19 from chest X-rays with 90% accuracy. Companies like Gauss Circle use computer vision to monitor blood loss during surgery, saving billions of dollars annually. These advancements show the real-world benefits of deep learning in healthcare. Imagine waking up and asking your smart device about the time, weather, and your schedule. The device responds in natural language, not programming code. This is possible thanks to natural language processing (NLP), a subfield of AI that enables machines to understand, analyze, and generate human language. NLP powers many smart applications we use daily. NLP allows computers to process, analyze, and understand human language, which is a key aspect of intelligence. It uses algorithms and methods to handle text input and produce meaningful outputs like labels and semantic representations. NLP is essential in applications such as e-commerce, education, finance, entertainment, healthcare, customer service, and marketing. NLP is widely used in products and services, creating opportunities for experts in the field. For example, sentiment analysis helps monitor social media, and search engines use NLP to analyze queries and provide relevant information. NLP also powers query correction and recommendation features, enhancing user experience and making information retrieval easier. Search engines like Google and Bing rely on NLP to analyze user queries and deliver relevant results. When you type a famous person's name, the engine provides key information and news about them. NLP also corrects spelling errors and suggests alternative queries, making searches more efficient and user-friendly. After building a machine learning model, it's important to export it in a format compatible with your target platform. Not all extensions work everywhere, so choosing the right one is crucial. Teachable Machine offers options like TensorFlow, JS, and TensorFlow Lite for exporting models. Let's explore the differences and how to select the best extension for your project. TensorFlow JS lets you build machine learning applications in web browsers. It's compatible with TensorFlow APIs and uses JSON files for models. The Layers API makes it easy for those familiar with Keras, while the Core API handles complex operations like tensor declarations and memory management. TensorFlow JS integrates smoothly with web technologies, making it ideal for web-based deployment. While TensorFlow JS offers many benefits, it can face performance issues due to browser limitations. Modern browsers now support hardware accelerators like WebGL and WebGPU, improving performance. This makes TensorFlow JS a strong choice for deploying models on the web, leveraging local hardware for efficient training and inference. TensorFlow Lite is designed for running machine learning models on mobile devices and IoT platforms. It doesn't require a server, ensuring privacy and reducing latency. TF Lite models are small and efficient, making them ideal for mobile applications. Let's look at some real-world examples of machine learning on mobile devices. Traveloka OCR uses machine learning to recognize identities from ID photos, speeding up data entry and reducing errors. Google Translate's instant camera translation helps tourists understand foreign languages by translating text and images. These applications show how TF Lite makes everyday tasks easier and more efficient. For deploying TensorFlow models on mobile devices, it's important to understand TF Lite's architecture. TF Lite supports multiple programming languages including C, C++, Swift, Java, and Python. After training your model, you can export it as TF Lite and integrate it into your mobile application, making machine learning accessible on the go. TF Lite comes with APIs for various programming languages, making it easy to integrate machine learning into mobile and IoT applications. After exporting your model, you can deploy it on devices without needing an internet connection, ensuring privacy and efficiency. This flexibility is why TF Lite is popular for mobile machine learning. Behind deep learning, computers perform countless mathematical calculations. Let's break down the process from input layer to hidden layer and output layer. Using the MNIST fashion dataset, we'll see how each layer works to classify images of clothing, shoes, bags, and more. Understanding these steps helps you grasp how deep learning models learn and make predictions. Data preparation is crucial in deep learning. For image classification, each pixel value is normalized by dividing by 255, making it easier for neural networks to learn. The architecture includes input, hidden, and output layers, each playing a specific role. Let's see how these layers are defined and how they contribute to the learning process. In Keras, models are built using the sequential function, stacking layers to perform calculations and produce outputs. The input layer defines the shape of the data, the hidden layer processes it, and the output layer generates predictions. Activation functions like ReLU and Softmax help the model handle different types of data and tasks. Input layer in Keras uses the input shape parameter to define the resolution of training images. For example, MNIST images are 28 x 28 pixels, so the input shape is 2828. The flatten layer converts the 2D matrix into a 1D array, preparing the data for further processing in the network. Dense layers in Keras serve as hidden and output layers. The units parameter specifies the number of perceptrons in a layer. Activation functions like ReLU are used in hidden layers to help the model learn complex patterns. The output layer uses Softmax for multiclass classification, selecting the class with the highest probability. Each neuron in the network represents a perceptron performing calculations based on weights and biases. The learning process involves summing inputs, applying activation functions, and generating outputs. This mathematical approach enables the network to learn from data and make accurate predictions. Activation functions are essential for neural networks to recognize nonlinear patterns in data. Without them, networks can only identify linear relationships, limiting their effectiveness. Functions like ReLU and Softmax allow the model to handle complex, real-world data, improving its ability to learn and predict. Most real-world data is nonlinear, making activation functions crucial for deep learning models. Without them, networks would only recognize simple linear patterns like straight lines in regression. Activation functions enable models to adapt to complex data distributions, improving their performance and accuracy. After defining the architecture, the model must be compiled with an optimizer and loss function. The optimizer adjusts parameters to minimize errors, while the loss function measures the difference between predicted and actual outputs. Common optimizers include ADAM, and loss functions like sparse categorical entropy are used for multiclass classification. Once compiled, the model is trained on the dataset. The epoch parameter determines how many times the model processes the data. Training adjusts weights and biases, improving the model's accuracy. This iterative process is essential for building effective deep learning models. Running deep learning models requires powerful hardware. CPUs, GPUs, and TPUs are commonly used to handle intensive computations. Choosing the right hardware depends on the complexity of your model and the platform you're deploying it on. Let's explore the differences and benefits of each type. For local machine learning, GPUs automatically handle computations. However, cloud platforms have hardware limitations that affect costs and performance. If your model requires intensive training, GPUs or TPUs are better choices. Simpler models can run efficiently on CPUs. Understanding hardware options helps optimize your machine learning workflow. Developing deep learning models involves more than just building the model. You need to understand the entire process from data preparation to hardware selection. With the right tools and knowledge, you can create models that solve real-world problems and perform complex tasks efficiently. Congratulations, you've learned the fundamentals of deep learning, from neural networks and perceptrons to real-world applications and hardware requirements. With this knowledge, you're ready to explore deeper and build your own models. Remember, deep learning is a powerful tool that can transform industries and improve lives. Keep learning, experimenting, and innovating.